The most important geopolitical assets in the world range from maritime chokepoints and natural oil reserves to rare earth elements and the global reserve currency, but among them all stands the kingmaker of the world's technology juggernauts, TSMC. Without the talents that fuels the Taiwan Semiconductor manufacturing company, the inner workings of the screen you are watching this video on, nor the headphones you are hearing this through, may not be possible. That is a difficult claim to wrap your head around, but yes, an island nearly 13,000 kilometers from Washington, D.C. is responsible for the hardware success of the world's largest companies. In this video, we'll be diving into how the company came to be an international treasure, the engineering marvels that led to its kingmaker status, and its entanglement between the world's premier superpowers. But first,
we have to understand the true scale and origin of one of the world's largest contractors.
The iPhone 17, H100 AI chips, and the United States' F-35 fighter jets are all engineering feats in their own right. But their creators, Apple, Nvidia, the US military, do not manufacture the chips that these technologies heavily depend on to be the marvels they are. Instead, that work is outsourced to specialized foundries surrounded by the East and South China Seas. On soil comparable in size to Vancouver Island, these foundries operate under the largest semiconductor manufacturer around, and if they take a rest, so does the global economy. They come together to reinforce the grip TSMC has on semiconductors, with the company producing over 90% of advanced node technology, such as their 3nm process, the closest we have come to actual magic. This hold gives the contractor its kingmaker status, as many companies and governments rely on its expertise. However, prior to the 90s, the idea of outsourcing production and only designing the chip yourself was barely on the drawing board. If you wanted your own chip, you had to invest billions into the factories needed for such an endeavor, and this was the model Intel popularized. According to the company itself, a typical fab includes 1,200 multi-million-dollar tools and 1,500 pieces of equipment. Building these fabs costs around $10 billion, and timelines can last as long as 5 years, taking the effort of over 6,000 workers.
But it doesn't end there. This is what it takes to build the average Intel factory.
The heaviest cargo is the 50,000 kilogram chiller, the size of 12 average-sized male African elephants. Over 600,000 cubic meters of concrete poured, plus 75,000 tons of steel reinforcement, double what was used to build the Burj Khalifa. Over 1 million cubic meters of soil and rock removed, around the size of 400 Olympic-sized swimming pools. Over 35,000 tons of structural steel used, 5 times the weight of the Eiffel Tower, and over 9 million meters of cable, the distance of 214 full marathons. Now take that workload and replicate it 15 times. That's the number of fabs Intel has across the United States and 3 continents. If you wanted to build your own semiconductors, this is what you were up against. But an electrical engineer by the name of Chang did not believe in that norm.
His philosophy was centered around democratizing chip design. In the world he envisioned, customers could create a design of a chip they wanted and outsource the actual production to a neutral contractor. This integrity is one of the defining qualities of TSMC's relationship with its clients.
Unlike companies such as Samsung, which manufacture semiconductors but present a conflict of interest as they compete in the same industry as their clients, TSMC is dedicated to the craft of production. It does not have its own brand of consumer electronics, and as such, companies such as Apple and Nvidia feel safer giving their designs to this Taiwan-based company. After graduating from MIT with his bachelor's and master's, Chang had the option to work at one of 2 companies. The first was the Ford Motor Company. It was more established, safer, and perhaps what many of you would have considered a real job. But it paid slightly less than the alternative, Sylvania Semiconductor, the young division of Sylvania Electric Products. After calling Ford about a pay increase, Chang was greeted by a hot-tempered voice on the other end, prompting him to work at Sylvania. There, he would learn about semiconductors and transistors, the underrated foundation of modern technology, and he would experience the impact his colleagues had on the industry firsthand. Although he eventually took over the company's R&D department, his time there was a short stint, after which he would work at Texas Instruments.
He would work at the new company between 1958 and 1983, a span of 25 years. His focus was on the development of transistors for IBM, one of the first examples of a relationship between a client and its foundries.
He presented the idea of sacrificing short-term profit for long-term gain, which he proposed would result in higher profit margins and market share.
But toward the end of the 70s, as Texas Instruments moved its focus to more embedded systems such as calculators and watches, Chang would become disillusioned, as he was more concerned with the development of semiconductors.
At the start of the following decade, just a few years before leaving the company, he noticed that the output of Texas Instruments' Japanese factories was double that of its Texas base, leading him to believe that the future of microelectronics was Asia. Later in his career, he would become the head of Taiwan's Industrial Technology Research Institute, a non-profit with the aim of promoting technological innovation in the country. As the head of the organization, he founded the Taiwan Semiconductor Manufacturing Company, and as foreign businesses saw value in outsourcing hardware production to Asia, TSMC quickly became one of the world's largest chip makers.
From the start, TSMC was an initiative by the Taiwanese government to develop its economy and wider technology industry.
And it did so for some of the greatest engineering marvels to ever come out of advanced node manufacturing. But it began with normalizing the very concept of foundries. Prior to TSMC, when the world of semiconductors was a secretive Wild West and companies such as Intel kept their recipes to themselves, TSMC wanted to treat manufacturing like Lego. This would mean a uniform set of instructions, known as a process design kit, for clients to follow, with the promise of a working chip at the end. During the era of this Wild West, it was standard practice to use aluminum for internal wiring.
The metal has the fourth highest conductivity of all metals, and it is a highly efficient choice for long-distance transmission. However, it only possesses around 60% of the conductivity of an even higher ranked metal, copper.
While aluminum is 30% lighter than copper, the latter is more durable, conductive, and less prone to overheating. Copper's higher conductivity also means that less of the material can be used, compared to aluminum, where larger quantities are needed to achieve the same result. TSMC took this route, attempting to convince the industry that foundries were the way to go, with the development of 0.13 micron technology. If you have watched my recent videos, then you would have heard of figures such as 220 nanometers, 22 nanometer, 14 nanometer. Those all describe the size of a chip's transistors, and micron is just a different unit of measurement for that size. TSMC's 0.13 micron technology was a 130 nanometer processor, using all copper, a material science nightmare given how electrons tend to spill over into silicon. To visualize this better, a single strand of your hair is about 80,000 nanometers. For decades, we have been working with transistors invisible to the naked eye.
The proven model TSMC was trying to disprove was 0.18 micron technology, which used aluminum for less efficient wiring. It also showcased shrinkage of up to 72%.
In the world of semiconductors, the smaller you go, the more transistors you can fit on the same silicon wafer, an ultra-thin slice of metals such as crystalline silicon. In this context, the 72% shrinkage of TSMC's 0.13 micron chip, compared to the industry's 0.18 micron processors, meant that its transistors were 70 to 75% smaller, Combine that with the efficiency of copper and the fact that the company developed this independent of joint partnerships, and you get a gamble that disrupts global supply chains.
All this was incredible at the time, but to understand how we went from hundreds of nanometers to talking about 2 nanometer chips, mainly a marketing term but almost true to the size, and nearly the diameter of 10 atoms, we have to look at a process known as lithography.
If you're an art connoisseur, the name might bring up images of Charles Marion Roussel or 20th century maps of the Russian Empire, but it is also recognized by engineers, just in a very different context. The early 2000s were a crisis for microelectronics. To oversimplify, lithography in engineering is the use of invisible wavelengths of light to print intricate geometric patterns onto silicon wafers. Think of those sci-fi or neon green lines you see on Hollywood's stereotypical circuits and microchips.
Those lines represent 30% of the cost of manufacturing a chip, and they are printed using a polymer called a photoresist, which is a protective mask layered upon the chip. The light used in this process can be called an excimer laser.
At the start of the 21st century, the laser being used was a 193 nanometer argon fluoride light. Using an example from ASML, to print small transistors, the industry had to work like an artist, switching from a marker to a fine liner pen for greater precision. The plan was to switch from that argon fluoride light to a more precise 157 nanometer fluorine light. However, the problem was, the further you shrink transistors, the more you defy physics. This was a wall for the industry.
That was until a TSMC engineer by the name of Baron J. Lin pioneered a process known as immersion lithography.
When light goes through water, particularly dense, ultra-purified water, it slows down and bends, compared to traveling in air. This is where the term refractive index comes in. A refractive index is the ratio of the speed of light in a vacuum compared to the speed of light in a given medium, such as air or water.
Because the refractive index of water is greater than that of air, light loses its wavelength by over 75%. You can test this out yourself by dipping a straw or a similar object into a cup of water, and as you can see here, light bends around the pencil.
This was the factor that led to the development of immersion lithography. Light goes through a series of lenses, then purified water, and finally the photoresist mask to print the geometric pattern. This saved billions and allowed TSMC to achieve 90 nanometers and less.
But even this, going smaller, comes with its own set of problems.
Let's take a quick look at quantum mechanics. In the world we live in, you can run into a brick wall, but at least 9 out of 10 times you will not go through. However, when we try to produce technology the size of atoms, those rules no longer apply. This is because of a phenomenon known as quantum tunneling. If I tried to fully dive into it, we would be here all day, but we can still get the gist of it. At the scale of, say, 22 nanometers, the electrons in a transistor are kept in place by energy barriers, the equivalent of the brick walls we have. These electrons cannot go through this barrier because they do not have enough energy to. But as transistors become smaller, the probability of these particles passing through, or tunneling, goes beyond 0.
These aren't even particles per se, as you might imagine in the traditional sense, but instead they act like waves, and when those waves overlap with the energy barrier, that particle is more likely to appear on the other side.
While quantum tunneling is responsible for nuclear fusion in our sun, on a smaller scale, it's more problematic. When electrons bypass those barriers, you leak electricity and risk heat generation. It's one of the reasons Moore's law, an observation that the number of chips that can fit on an integrated circuit would double every 2 years, is slowly coming to a halt. Those transistors follow the thin field effect architecture, whose physical limit is at 3 nanometers, which TSMC has already achieved. TSMC brought this architecture to mass production, but is moving away from it for a gate-all-around thin field effect architecture for the 2nm node, which will provide 10 to 15% more speed at around 30% less power than their current 3nm counterpart.
But the marvel that essentially solidified TSMC's kingmaker status was the CoWoS model.
CoWoS, short for chip on wafer on substrate, is one of the greatest innovations by TSMC in the 2000s, and the packaging of Nvidia's latest H100 chip. Why? That's because CoWoS allows you to fit the GPU and high bandwidth memory chip next to each other on a silicon interposer, essentially a miniature motherboard. This allows TSMC and its clients to bypass the growing physical limits of scaling down transistors, allowing for more advanced chips such as the H100 to be manufactured.
This kingmaker status is also the foundation of Taiwan's silicon shield. Let me explain.
If you look up Taiwan and look right to the Wikipedia summary, you will see its official name as the Republic of China. You look up China, and its official name is the People's Republic of China. So, two Chinas? Well, it's not that simple. It's not a history channel. But to understand why the silicon shield exists in the first place, we have to look into the relationship between these two nations. Explained like in 5, Taiwan is the original China. Not the China that has existed throughout history, but the China we had at the start of the 20th century. They were in mainland China, while the island was a Japanese territory. After the defeat of the Axis powers in the Second World War, Mao Zedong and his Communist Party captured the capital of Beijing in 1949, claiming and forming the People's Republic of China.
For better accuracy, the Republic of China was the original government of the mainland and now presides over the island of Taiwan.
Given their circumstances, Taiwan was much poorer than the mainland and feared an invasion from the much larger communist China in the name of reunification. That narrative is still around today, and to keep China happy, Taiwan keeps its name as the ROC, and we call it a province, the Chinese Taipei, at the Olympics. But just across the Pacific Ocean was an even greater power, the United States. They were expanding their military presence in the Middle East to primarily secure oil and other natural resources. If you look at Taiwan, they don't have much to offer to the US in terms of those resources. So what if they tried to make their own?
This was the plan behind TSMC. The Taiwanese government was its first major investor, raising over $58 million in a joint venture with Dutch healthcare company Philips. And even today, it is still the largest individual shareholder in the company.
As TSMC grew, Taiwan's silicon shield was shaped around a geopolitical truth. If the whole world relies on your technology, there is a vested interest in your safety and economic suicide in challenging it. It is a bold claim, but in a practical sense, TSMC is the Taiwanese economy, with a market cap of up to $2 trillion, higher than that of Walmart, Tesla, or Meta, as of the time of this upload. The world's three largest economies, the United States, European Union, and China, are all dependent on this island for its advanced node technology, which it produces over 90% of the global supply of.
Making a wafer is the most complicated manufacturing process in the world. I can't imagine anything else more difficult than this.
Up to 4,000 precise steps, and just one slip,
You're done.
inside the clean room, a tightly controlled environment where chips are created, tested, and perfected. It takes workers like Sterling to make sure what's promised is delivered. He's an EBO mask technician, essentially quality assurance.
What I'm doing is on EUV is basically an electric ultraviolet beam. That's EBO, electric ultraviolet beam. And I'm looking through this scope and I'm looking at all these different things. Again, trying to make sure that exactly how we have our pattern is how they have their map.
TSMC's first fab is up and running in Phoenix, making 4nm chips, and they're just getting started, announcing earlier this year another $100 billion investment to ultimately have 6 fabs, a research and development center, and 2 advanced packaging facilities.
Even as challenging as this may seem for China, it is still a superpower.
If Taiwan is the world's laboratory, then China is its factory. That status grants you the ability to economically coerce even larger powers, and as such, historically at least, most nations have remained ambiguous on what actions they would take in the event of an invasion. Measures are being taken to diversify TSMC's capabilities, such as the CHIPS and Science Act, enacted under the Biden administration, which provides just under $300 billion in funding to semiconductor initiatives, such as the company's Arizona plants. Outside Arizona, the company also has fabs in Washington State, Kumamoto, and China. In the event of an invasion, a kill switch for these fabs could be used as a scorched earth tactic, rendering fabs in Taiwan and China unusable, and transporting talent to the US and Japan. But going back to the topic of strategic ambiguity, a historical precedent was defined when Japan's new Prime Minister, Sanae Takeichi, designated a would-be invasion as an attack against Japan, and thus a threshold to mobilize its armed forces in the name of self-defense.
Well, Errol, as you say, it's without doubt the most serious diplomatic clash between China and Japan in years. It began early this month when Japan's newly elected female Prime Minister Sanae Takeichi was asked in Parliament what would constitute the deployment of military force in Japan. Her response: if China attempted to blockade or seize Taiwan. Now, geographically, Taiwan is about 68 miles from Japanese territory. As we know, Beijing claims Taiwan as its own. It's refused to rule out using force to take control of the democratically governed island.
考えに一切変わりはございません。いかなる事態が、存立危機事態に該当するかということにつきましては、実際に発生した事態の個別具体的な状況に即して政府がすべての情報を総合的に判断すると。
China did not take her words so lightly, resorting to sanctioning Japanese imports and even forcing a Japanese artist, Maki Otsuki, off stage in the middle of her concert, and forcing its policy on also sanctioning cultural exports. With the tension between China and Taiwan reaching a boiling point and the onset of global uncertainty in general, diversification is the smartest move to make while we still can.
Bringing the magic that defines TSMC to more secure regions is an insanely difficult task. Much of the production of advanced node technology is relatively cheap because of Taiwan's lower valued currency, the new Taiwan dollar, compared to the higher valued US dollar. That, and teaching the skills required for semiconductor manufacturing to American and Japanese engineers, plus finding a way to export Taiwan's grueling work culture that makes all this possible in the first place.
While the Chinese invasion of Taiwan will very likely be a war that only ends in the loss of China's technology sector and the progress it has spent decades making, it is still more important than ever to be wary of Beijing's stance, especially knowing it could plunge the global economy into a dark age. Do you think Taiwan's engineering magic is even capable of being exported globally? Give your answer down in the comments. Thanks for watching, and I'll see you in the next one.